Alright, so here's the beam that we need to do with singularity. So we'll have our two impulses for our reaction, we'll have our impulse for that point load there, and then we'll have our step function for that distributed load. And that means that the impulse, of course, is this -1, and the step function is 0. So we're not going to worry about those for right now. Let's just get these written for the beam here. Alright, so this is Q equals R1 at x minus 0, because we're starting at 0 to the -1. And that's in the positive direction because it's going up. And then we have our distributed load, which is coming down, so it's a minus. I'm going to call that W, and it is x minus 0, because that's where we're starting the distributed load. That's at 0. And then we have the point load coming down, so that's another, that's our F, I believe, labeled 200 pounds. That was x minus. Now that was happening at 72 inches. So I'm going to be converting everything to inches. That's 72 inches. And then we have our other reactionary load, R2 x minus 96. And that actually, this one is to our -1, this is to our -1. So this is our loading function. Alright, now this guy here, we'll never use it, and we can leave it in there, but because we're looking between 0 and 96, this thing will never be more than 96, so this thing will never be more than 0, and so it'll always evaluate to 0. V is, now these are, you can't just think about these as regular integrals. These are singularity integrals, and so this has a special definition. This is x minus 0, and I'm going to leave the 0 in for the moment, just so we can see, we can understand that it's really evaluated. This is evaluated at anything below this is 0, and then anything above this is our definition here. So this will be 0, this will be W x minus 0 to the 1 minus F x minus 72 to the 0 R2 96 to 0. And of course we have plus C1, and then our moment R1 minus 0 to the 1 minus W divided by 2, because we've started up into the positive range here, so it's x minus 0 to the 2 F minus 32 to the 1 plus R2 x minus 96 to the 1 plus C1 plus C2. Now we're told that as long as we have R2, R1, and R2 in this equation, these will always evaluate to 0. So these will always be 0. Alright. Now we have our angle. So if this is theta equals, now we're getting into our R1 divided by 2, x minus 0 to 2 minus W2, so this will go to 3, so this will have to go to 6, minus 0 to 3 minus f x minus 72, 2, so this gets divided by 2, and then R2 divided by 2, x minus 96 to the 2. And we just leave that off. Oh, and I do have, to get to the angle function, we also have the 1 over EI out here. Now, for our deflection, now, I also have plus C3. And this will actually probably equal something, so we can't leave it out. So put my 1 over EI over here, and these are, of course, these are constants, so they're outside of the integration. And I'll have R1, this goes up to 6, x minus 0 to 3 minus W24, x minus 0 to the 4th minus f over 6, x minus 72, 2 plus R2 by 2, 96. Oops, this goes to the 6 plus C3x plus C4. Okay. So this is our deflection function. Now, the thing that you have to realize is that you can't just plug this into Mathematica and have it evaluate it for any x, because these are actually decision points. So these don't matter because they're all less than, anytime we have an x will be more than 0, so these will always be positive, and so they're always going to evaluate out for any x. But this one is not. This will be 0. This entire argument here will be 0 until x is greater than 72. When it becomes greater than 72, then it's x minus, 73 minus 72, whatever, squared times our force here. So that's an important part to think about. So in Mathematica, Matlab, I did a little function that was able to evaluate this, and if this was positive, then it would return this value squared and then multiply times that. So that works pretty good. So we have two boundary conditions that we know about with this deflection. One is that when x equals 0, we know that y equals 0. So we can plug that in here, and if you do all that algebra, plug in all our zeros, x's, this will all cancel out, and we'll be left with C4 equals 0. I'm not going to go through that, it's really long. The other boundary condition we know about is x equals 96, which is the end of our beam. We know that y equals 0 at that point as well. So if you put 96 in here for everywhere we have an x, and then solve for C3, you'll come up with C3 equaling somewhere around 225, 600, I believe, something like that. Okay, so once you get C3, you know C4 is 0. You always know this thing is 0. So then you can, if you have a program that will evaluate this and only evaluate it when x is greater than 72, then you can do a plot for this. Otherwise, if you're just, finding a particular deflection at a point, you just plug it in, and if you're, let's say we said we wanted to know y at 48, and that evaluates to a negative 0.5151 inches. So you just put 48 in there. Now this would evaluate to 0 because it's less than 72, and this would be negative, so it would be evaluating to 0. And then you just are left with this expression and these two. And then you solve it, and that's what you come up with. So I hope that helps with the whole singularity concept. Actually, I can show you what I did in Matlab. So I have a singularity. I wrote a little function here, singularity f3, because it's to the third. It takes in x and a, and then it evaluates if x is greater than a, then that'll be 1. So this times 1. So this is the value that gets returned. Boy, it doesn't want to stay focused on this, does it? And then my functions, so I have my C3 in there, I, E, all that other good stuff. And then I did an anonymous function. And so when I was calling that section there, where I needed to decide whether that was true or not, I use that function there. So when we run it, and we need to go and run, then I can make a plot. So I've done a nice plot here of the deflection. All right.